Alright, so welcome to this lecture on perturbation theory in quantum mechanics. So we're going to present the general framework, including first and second order corrections to the energy, and then we'll look at the most important application, which is perturbation by a constant electric field, and that leads us to the polarizability. And the concept of oscillator strength that I will talk a little bit about, and the sum rule there, if we have the time, and maybe also a little bit about time dependent. Those of you who have taken the quantum materials course know about this stuff to some degree. So, but first of all, we'll do stationary perturbation theory. So the problem we want to solve is something like this. So we have a stationary eigenvalue problem, and the idea here is that this, in some rather vague sense, is a small perturbation. This is the perturbation which might represent the electric field perturbing our system, and we assume that this is a small correction. So in that sense, these eigenstates are going to be close to one of the unperturbed eigenstates, the ones that you have without the electric field, and the eigenvalues are going to be close to the original eigenvalues. And we of course assume that the original states are easily solved. So let's say now that the eigenstates in general can be written in some series. So I'll write it like this, plus, plus, plus. So this simply means, this superscript here means the power of the perturbation. So you can think of this as the power of the electric field. So this is what you get without an electric field. This is the first order correction due to the electric field. So this will be proportional to the field, to the first power, and then you have a second power correction and so on. And the same thing, of course, for the eigenvalues. So there's the unperturbed eigenvalue, there's the first order eigenvalue, second order, and so on. Right, so again, these corrections are assumed to be small. So what I'll do is I will plug these expansions into this and this first of all. So H0 plus H1 on all of my terms here, plus 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 equals there's a lot of writing in this exercise, as you can easily see. Like this. So this is still exact, right? Because I include all terms for the wave function, all terms for the energy. But now what I will do is pick out terms of a particular order. So I'll start by looking at zeroth order. So that amounts to simply saying that now there is no electric field, there's no perturbation. So this means that this is not there, this is gone, this is gone, this is gone, and so on. All these corrections are gone. So what I'm left with here is the zero order eigenvalue problem here, which of course is nothing but what we've been doing all along, right? This is the standard problem if you think of this as an atom in an electric field. This is just the original problem for the isolated atom, the unperturbed problem. And this is the problem which we assume we already solved, and we did actually. I'll be using a slightly different notation along the way. So this zero order solution I'll just denote by this Dirac ket there. So that's easy enough. We assume that this is done already. So next up, of course, I'll be collecting first order terms. So now I look at this equation and I think to myself that there's going to be terms with all kinds of powers of the electric field. So there's 0 order terms which are already collected, but there's also going to be a bunch of first order terms. So for instance, this is first order because it doesn't include the electric field. So if I take that part here, then I need to pick the first order term from this expansion here, so that's going to be this guy. Then I can take this guy, which is already first order, right? This includes the electric field. I didn't write that, but in an electric field, just to make it this more clear, we'll get back to that, but the perturbation is simply the electric field dotted onto the position of the electron. So this is clearly proportional to the electric field. So if I take the first order term here, then I should have 0th order term in that part, so that's going to give me this. And similarly, of course, on the right-hand side, I take 0 order part here with first order wave function and first order there with 0 order wave function. And now that we're at it, we might as well collect second order term. We're going to use that a little later. So that's going to give me this one. And so that's second order, this with this guy here. And also this with this is also second order, right? There's a factor of E field here and another one here. So I get an H1, psi1, and on the right hand side, and now I'm going to get 3 terms. There's the 0 order term for the energy, then there's the first order energy with first order wave function, and finally second order 0 order wave function. So that's all I get at second order. Well, you can easily see how I could continue this to arbitrary order if I wanted to. Right, so we assume that this is already solved, and this means that we can now look at this one. So what I will do, I will take the first order equation there. And then I will, let's say schematically, I will apply the bra here, the conjugate of this one, from the left onto the entire equation there. So let's do that. So I get my n h0 1 plus, so that's this term here, plus this next term, which I'll write like this. Over here I get, this. And then this term here, and of course we assume that these are orthogonal. Maybe I should write this, right? That obviously n, m here are orthonormal. So this is just going to give me en1 over there. And now what I will claim is that this term equals that term. Why would I claim this to be true?
They're both equal to 0.
No. Well, in fact, they will be, but we don't know that yet. That you were right, actually, but I mean, why did you say that?
Because you can take this H0 and apply it on n, and then you would get E sub 0.
Yeah.
And because they're orthonormal, it will be 0 on the right hand side.
But this is not. It is actually, but we don't know that yet. We don't know that this is actually orthonormal to this one. I mean, this is not another one of the unperturbed eigenstates. This is a correction to the nth state. So So we don't actually know that these two are orthogonal yet. They are actually, but anyway, even if they're not, it's still true that this term is definitely the same as this term.
Well, that's only true if the Hamiltonian doesn't do anything to the first.
No, it's because this H0 is Hermitian. Casper?
Yeah, so can we make it act on the n?
Right. You
And
can
then get
think of it
theorem of-
exactly as if it's acting to the left. You know the drill. I think you invert this, and then you're supposed to replace this by its conjugate, its Hermitian conjugate. And then you should take the conjugate of the entire thing, but this is Hermitian, right? So that's just going to be itself. Then it can act on this guy, producing the eigenvalue, and therefore that will cancel this term here. So it's because H0 is obviously Hermitian, so that gives us this very nice and simple result that the first order correction to the energy is simply the matrix element using the unperturbed eigenstate and then the Hamiltonian. It's sort of just the expectation value of this perturbation. So you can think of it as if the system remains in its original state, then you apply this perturbation, and then you ask, okay, what is the average of the effect of that perturbation, even if the state is not changed. So that's the first order correction for the energy. And now we are going to talk about the wave function, the first order wave function. And to that end, we will need the normalization. So we want the perturbed eigenstate to be normalized still, obviously. So I would like this to remain 1, even including the perturbation. So I will plug in now my expansions, my expansion here. So this implies that 1 equals, well, I have a 0 order term, which is this. Then I have two first order terms n1 and 1n, and then I have higher order terms like n2 and a bunch more. But now the point is that this, of course, is itself 1, because the unperturbed states are also normalized. So all of these corrections here have got to be 0. And the only way this can happen is if the terms are 0 at each order, right? Because you can think of this as sort of a polynomial in the electric field here. So this is the first order term in the electric field. This is part of the second order term in the electric field. So it's like you have a huge big polynomial over here, which is going to be identically 0. And the only way a polynomial can be identically 0 is if each term is 0. So this, the combined first order terms will be 0. There are 3 second order terms that are also going to be 0 combined. And that's exactly the point, right? This shows, I mean, this is just a complex conjugate of this. So this means that this is actually 0. So that's exactly what was said before, but now we know why. That these are actually orthogonal. And then you can see what goes on up here, but that's not going to worry us right now. So what I will do now is look at my first order equation again, but I'll try to solve for the wave function. And what I will do is write this unknown wave function in terms of what I already know. This is what's called a sum over states. So I will expand my unknown wave function in terms of known ones. So let me just write it like this. So that is the idea, that we build the unknown function from the ones that we know already. So now the question is, of course, what are these coefficients here that we need to apply to construct this superposition to get the perturbation. So that is what I'm going to do. I'm going to plug that into this first order equation. So I get, let's see here, summa m, cn m, and then h0 on m here. That's the first term. And then I get this term, which I know already, h1 n, and on the right hand side I get en 0 summa m cn m m, and then this en1, which I already calculated, and then n. And then what am I probably gonna do?
Use the equator delta.
Yeah, that's right. So I will use the fact that all of these states are orthogonal. So I'll sort of apply in bright. There's also another thing I want to do, because when h0 acts here, obviously it's going to give me em0 on the m state here. Yeah, and maybe I can just fit it in. So you can imagine if I just take an arbitrary m bra and apply from the left, then I will just pick out one term in each of these sums here. So in the first one here, I get C in M, E in 0, and then here I get M, H1, N. Over here, again, when I apply this bra, I pick out the one term, so I get E n 0, C n m, and then there's this final one, which of course is E n1, and we could write delta nn. And that basically tells me what I need to know. Because now let's assume first that m is not the same as n. Then this term is gone, obviously. So I can easily isolate if I move things around. And what I find here is that Cnm is then gonna be this m h1n divided by en minus en, I guess. Right. So that's all good and well. But now apparently I would have a problem here, because this obviously doesn't apply if m is the same as n, right? Then I just get the identity, because then this term is the same as this term, so they just cancel. And this term, of course, is still the same as this one. So that doesn't give me any further information. But this is where my orthogonality here becomes important, because this tells me precisely, right, that I know this is vanishing, right? So if I do that, since they are orthogonal, this just tells me that this is actually the same as Cn. So since they are orthogonal due to normalization, this term, the diagonal term, vanishes. So actually, when I'm constructing my first order correction to the wave function, it does not contain the unperturbed state. So I'm going to sum over all m different from n, this m h1 n over, and here let me already here write this as EN M. And then here's a M. So by this ENM, I simply mean the difference between unperturbed eigenvalues here, this energy difference. So that's the general way of constructing the first order correction to the energy. So it's built from all the unperturbed eigenstates except the one that I started from. That does not contribute to the correction there. Because, as we showed, they are orthogonal. And you can obviously see that whether or not a particular state contributes a lot here, well, that depends, of course, on these two factors. So if the two states are close in energy, there's a chance that this will contribute a lot, because then this energy difference is small. But obviously also this matrix element here in the numerator has got to be non-zero, and that's what's called the selection rule, that some of these matrix elements are probably going to be zero due to symmetry, and this means that there are some of these states that don't contribute to the correction. And for instance, that always happens in atoms with electric fields. A lot of these contributions are vanishing, and that phenomenon goes under the name selection rules. Right, so let's then finally look at the second order energy. So we'll use the second order energy and do more or less exactly what we did up there. So I will apply n from the left on this second order equation that I have here. So again, I get n h0 n2 now. And then from this term here, I get an n h1 on the 1 correction. And then here I get E n0 n2 plus, let me just write everything out. And then this guy there. So we already figured out that this is gone, right? Still orthogonal. And what else? What else is gone? Good.
Like before, we let the H0 go on n and then remove.
These two are, so they're not zero. Definitely not, but they are equal, and therefore they will cancel. So that leaves us with this very nice result, that the second order correction to the energy is simply this, this should be H1. This matrix element. So you need the first order correction to the wave function, you need your perturbation, and you need the unperturbed wave function. And then of course it's just a matter of plugging this guy in here. And you see that, well, when I do this, right, I'm going to get an N, H1, and M, which is the same as this one, except in the reverse order. So I simply get E sum M different from 0, and then here N, H1, N squared divided by which is the famous second order correction to the energy. So it follows this pattern very much. You can see that the terms that are going to contribute there are again those that are close in energy to my original state, barring these selection rules, obviously. Another actually quite important thing here is that if we look at the ground state, right, so if n here is the lowest one, then all of these denominators here are going to be negative. and the numerators, of course, are positive. So for the ground state, no matter what the perturbation is, it could be this, but otherwise it's definitely not positive. So every perturbation will lower the energy at second order. And in many, many cases, the first order correction is actually zero by symmetry. So this is the dominant correction, and you'll see that for the ground state, it will always lower the energy. Right. So before we have a break, let's talk a little bit about this very important application, which is normally called the Stark effect. So this is just the perturbation by electric field. So the way this comes about is, of course, that we can start by the classical level, where we would say that the change in energy implied by an electric field is minus the dipole moment dotted onto the electric field. And the dipole moment of a charged system is in general just the sum of all the constituents, let's say I, and then the charge of the ith constituent, and then the position. So this is the general dipole moment of, let's say, a molecule with several charges. But if we have just a single electron, then obviously the dipole moment of that electron is just its charge, which is minus E times R. So for a single electron, this implies that the change in energy is E and then the field dotted onto the position, which is precisely what we had up there. So what I'm going to do is just promote this to an operator, but that's easy enough because the position is its own operator, if you like. So this simply becomes the Hamiltonian as an operator. There's no change there. So it's basically the position that we need to consider, and we can of course choose a coordinate system in which the electric field is along some, let's say, z-axis. So my field points along z, which of course implies that the perturbation is just E times z. So what I need, let's say if we look at the first order correction, is then, apart from this E, it's going to be the matrix element of the z component of the position, if you plug that in the expression we had up there. But assuming this is an atom or something symmetric, what about this? So of course, this is nothing but the average of the z position of the electron.
And it's symmetric?
It's symmetric. It's an atom. It's a spherically symmetric atom. Yeah,
well, it's just zero then.
It's gonna be zero. Which, and in general, what we would say is that this is right. This is minus d0 dot the electric field in general. And if I do this, then this d0 is then minus E, and then the average of R itself. And this is what's known as the permanent dipole moment. So what this tells us is that a spherically symmetric atom does not have any permanent dipole moment. But that's a result of symmetry. And obviously, if I did something similar for, say, a water molecule, then there's no symmetry. I mean, there is a symmetry if you go between the two hydrogens, but there's no symmetry in the other direction. So a hydrogen atom definitely has a permanent dipole moment. Right? Then for a hydrogen, sorry, water molecule definitely has a permanent dipole moment because the average of this position is not zero by symmetry. But for isolated atoms and other symmetrical structures, there is no permanent dipole moment. So we need to go to second order. And what we would normally say, again, let's if we just think of it classically, we would say that, okay, so there's no permanent dipole moment, but there's gonna be an induced dipole moment, right? So once you put that atom into the electric field, the electron cloud will be displaced. The electrons will move in this, actually the negative direction, right? If the field points like this, then an electron which is negatively charged will be pushed in the opposite direction. So this disturbed electron cloud does have a dipole moment, which is an induced dipole moment. So what we would say in general is that D is at first order is some quantity times the electric field. So there's going to be an induced dipole moment which at lowest order is proportional to the electric field. You can have higher order, and so you can have something like field squared or cubed and so on. This alpha here is what's called the polarizability. The name says it all right because it tells you how easily you can polarize a particular system. How, for a unit field, what is the induced dipole moment? That's exactly what is embodied in this polarizability. So if we do that, then you could say, okay, so now I could think of this atom as being initially in its unperturbed state, and then I slowly increase the electric field. And what energy is then stored in the atom? Well, what again I would have let's say a dE, which is minus the dipole moment dotted onto a small change in the electric field, right? So if I increase the electric field from 0 to some infinitesimal value, then that will increase the energy by this much. And the associated dipole moment would be this induced one. And then so I start from 0 and then I end up with a small induced dipole moment. And then I can increase a little more and so on until I reach a final finite field strength. So in that way, the full energy that this takes will be minus alpha and then actually integral of the field like this, right? So once I start increasing the field, I induce a dipole moment, so I'll get a little more energy back when I increase the field even more using this minus here. So it builds up like this. And what you can see is that in the end, this is just going to give me minus a half, like this. And so that's the final energy stored in that atom in an electric field. Because you should think of it as building it up from a field of 0 to some finite field, and initially you get very little because there's no dipole moment, but as you increase the field, the dipole moment increases, and that gives you this final result. So a field, or an energy which is proportional to field squared in the end, and again this polarizability is the constant of proportionality. And now we can, of course, equate that to what we did over there for the second order energy, which I might write here. So I also said that En0 in this electric field is this sum of m different from 0. So I have my m and then my perturbation, which is E, let's say, Z. This divided by m. So if I compare those two here, what I see is that the polarizability is just twice some m different from 0, m, I can pull a factor of e squared out, set n squared, and then let me write this as em n. Right, so because I have a minus here, but I can get rid of that minus by inverting that denominator there. So this again will then be a positive. This is greater than 0 for the ground state. The polarizability of the ground state is always positive. So that's something we're gonna look a little more at, but before we do that, I would like to actually rewrite this in a slightly different way, because we could introduce what's called an oscillator strength. So as the name suggests, this is a measure of the importance of a particular transition, the strength of a particular transition between this unperturbed state and the nth state. So I could introduce this G, let's say Nm, as, well, I want this matrix element here, M set N squared, and then I want the energy up here, E M N, and then I also want actually an electron mass divided by h bar squared, I guess. This is, you might see that this is a dimensionless number. If you see that, so this, if you look at the inverse of that, you get an h bar squared divided by mass times distance squared, and that's an energy. So this is the ratio between two energies. So this is a dimensionless number. And in terms of these oscillator strengths, I then get still my 2 here, then I have my e squared, and then I of course I need to compensate for those. So I get this electron mass, but then otherwise m different from n, and now the G N M G N M divided by E in N squared. So that is just a funny way apparently of rewriting this. But the important thing is that, again, these are dimensionless numbers. And what we'll show after the break is that when you sum them, if you sum over all m, then this is actually unity, it's 1. So there's clearly some kind of bound on the largest polarizability that you can find, because these oscillator strengths must sum to 1. So you cannot have a bunch of transitions that are all extremely intense and giving lots of contributions to the polarizability, because if one is very large, the others are definitely much smaller. I think they sort of share the combined available oscillator strength. And if you do this in a classical calculation, you would find there's just one term here corresponding to this unity. That's what you would find classically for a classical electron. But quantum mechanically, the polarizability is sort of constructed from terms with different m, but all these different transitions between n and m share this oscillator strength in the sense that the sum value is 1. What I intend to do now is briefly demonstrate this result. This is actually normally known. It's not me, but another Thomas. the Thomas Eiche-Kuhn sum rule. And the starting point is actually looking at the commutator between the Hamiltonian, the unperturbed Hamiltonian, and then this position. Let's again just take the set coordinate, and assuming this acts on some state here, and the Hamiltonian has the kinetic energy and the potential energy. Obviously, the potential energy will commute with set, but the kinetic won't. So I get, if I let's take this. Today we are reinstating h bars just for fun, but this means that I have the second derivative in front in one term, and then the set coordinate, and then in the opposite order over here. You actually saw this in Quant2, but we'll just repeat it here. So the point is, of course, that it makes a difference whether this set is to the right of the derivative or not. So over here I need to differentiate a product twice. So I should differentiate this twice, that's going to give me 0. Then I will differentiate this guy twice. That term will of course precisely cancel this. But then I have the mixed term where I differentiate this guy once and this guy once. And that's the remaining term. And then I get 2 of those. Right? So I get minus h bar squared over m. And then this guy differentiated once, that's just 1. And then this guy. So second derivative on this guy. And this we can recognize if well, what I want is to write this as h bar over I dz on my wave function. So if I do that, I will probably have an h bar over m left, and since I have a minus here, well, maybe I should just put another I down there. So this, of course, is the momentum. Right. So the commutator between the Hamiltonian and the position is basically the momentum. And this has a lot of implications. You might remember these Ehrenfest sentences, which tells you that this is related to the time derivative of the position, which is basically velocity, and you see that that's what we get over here, because momentum divided by mass is also velocity. So that's one important relation. Another important relation is precisely the commutator between position and momentum, which you might remember. This is exactly just IH bar, this famous Heisenberg relation. So what I want to do now is use those 2 commutators. So I'll start from this one. So now I could take the n matrix element of that commutator, and via this relation here, this is then h bar over I me, and then the matrix element of the momentum. But now instead of expanding over here, I can do something clever, because the left-hand side here, of course, is m h0 z minus z h0 n, equal to the same stuff. And then I can use the fact that, again, h0 is Hermitian, so here I let it act to the left, and here, of course, I let it act to the right. So when it acts here, it gives me in em0 and when it acts here to the right, it gives me an en0. Still equal to all that stuff. So these, of course, can just go out. So I get an emn times mzn, that's all that's left, equals all that stuff. Or if you like, then I get this, finally, this relation between dipole matrix elements and momentum matrix elements, that this is h bar over I in E, and then the associated momentum matrix element divided by energy difference. So there's a simple relation between that matrix element and that matrix element that comes from the commutator. And this is something we want to use now. So if we look at the definition of the oscillator strength here, and sum over M. So let me do that. Sum here. So that is gonna give me this prefactor in E over H bar squared, and then a sum over M. And then the square of this matrix element, but maybe I will already now write that out in this way, because it's the absolute square, right? So I have this term times its conjugate, and then still E-M-N. That's what it says here. And now I will do two things. First of all, I will repeat this twice. So in order to compensate, I better divide by 2. So I could start by using this replacement over here. And you see that, of course, then this guy is going to cancel. So if I replace that term using this expression, I'm going to get h bar over I ME, and then this is left, N Z M, and then here I get an M P N. So that's one way of doing it. But I could also use this relation for that part over here. Obviously, if I interchange N and M here, I get N and M here, and then I get ENM in the denominator, but that's just going to give me a minus compared to EMN. So if I do that, since I have this, I get a minus, again, H bar over I M E, and then this is the term I replace, so now I get N P Z M. This one is left, M Z N, and again this is cancelled by that factor there. So now you see that I'm starting to get something that looks reasonable. Let me just check. Sorry. Actually, now I just see that I made a mistake. There's gotta be a 2 here. Yeah, and then this 2 is gone because I want this factor of 2 to cancel. So, sorry, let me just correct that. I just noticed that otherwise things won't add up. But now you see that these factors of 2 will cancel, and I'm just gonna be left with 1 over IH bar now. Like this will cancel 1, those cancel. I get a sum at M, and then here I get N, Z, M, M, P, N, and over here the opposite. And now I am almost done, because you can see that if I take the sum in here, I would get something like this. Right? When I sum over this thing here over N. Anybody know what that is?
It's equal to 1.
It's equal to 1, exactly. This is, sometimes it's called the resolution of states. It basically follows from, it follows from the conservation of probability. And if you say I have any state and it's a sum over some coefficients times my basis states. Here, so this is my, just call them Cm. And obviously by projecting here, my Cm are just m on psi, but I know that the square of all those is gonna give me 1, and that's the conservation of probability. So if I do that, I get precisely psi summa m, 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 and then another psi over here. Just summing these and plugging in this expression. But since this and this is 1, because it's the normalized state, this sum here in between is also 1. So that's what we're going to apply. And the sum of oscillator strengths here will give me 1 over I h bar, summa m, and so then the sum is gone. Here I get n z p n, and over here I get the opposite. And what is this? Maybe I can help a little bit by grouping terms. So I get an n and a z minus. So just taking the two terms together. Kasper?
It's the bracket of the commutator, so
yes.
it must be I h bar.
And therefore
1.
Exactly. So that's right. It's precisely 1. This sum, which I mentioned before. Something which I didn't really stress here is that obviously here I'm just talking about a single electron. You can repeat this quite easily for any number of electrons, and what you would find here is then that this actually sums to the number of electrons. So if you have a 3-electron system, this would sum to 3. But for just a single electron, this sums to 1. So that's this very nice and extremely general Thomas-Racky-Kuhn sum rule. All right. Just before showing you a few examples, I will very briefly talk about the time-dependent extension of this. So if we have a time-dependent electric field, then my perturbation is actually time-dependent, of course. So it's going to be E, Z, and then the amplitude times some cosine omega t. So we assume that this is a monochromatic electric field with a single frequency, which is of course the same as E, Z, E, and then 1/2 e to the minus I omega t plus e to the I omega t. So what happens in this case if you try to solve the perturbed problem is that now you get, of course, the time that you have to look at the time-dependent wave function, but to first order the wave function as a function of space and time, well, it's going to be the usual unperturbed state, which has this spatial part and then just varies in time as e, like this. Right? That's the usual time dependence of the non-perturbed system. But then due to the perturbation, we're going to get 2 terms, one with this correction, one with this correction. So there's going to be 1/2, something I might write as psi n plus, and then varying as e to the minus I e n 0 plus omega and then h bar t over h bar if you like, and then another term corresponding to that one over here, psi n minus e to the minus I e n 0 minus h bar omega divided by h bar and times t. So the two first order corrections due to the electric field also have a corrected time dependence. If you think of this En0 over h bar as the sort of fundamental frequency, you get these components that are shifted in frequency by plus or minus the frequency of the optical field. And it's not a very difficult exercise. You can basically see that if you look at this term here, everything you have to do compared to what we did previously is replace En0 by En0 plus h bar over there. That's basically everything that happens. So if you think back to this, we had this CNM. Suppose it is still here. So for that first term, you just simply add h bar omega to En0. So you get then m h1 n, which h1 in this case again is just e set e, and then you get here what I wrote as emn, and then plus h bar omega. So this is the plus coefficient that goes with this correction, and the minus correction is just the same except for a minus here. So you can go through everything and look at the induced polarization now, which of course will be time or frequency dependent if you like. And in the end, you get something which is really similar to what we have had already. You will find a frequency dependent polarizability, which is just in terms of oscillator strength, if we compare to what's over here at some point, it is gonna be something like E. Yeah, that's about right, yeah. So I messed up this factor 2 before, but that's, I actually did include it here, right? Because then I canceled that 2 there to get there. So that part is okay. So I think I will get E squared h bar squared over me summa m g n m, and then simply divided by ENM squared minus h bar omega squared. That is going to be the free.
Can m be equal to n in the sum there, since it's time dependent? Or?
No, m is still different from n. You can go through the exact same argument as before and show that this is still going to be